Here I have some calculations completed because some of them may take significant time. Okay, but I will start from scratch to show you how to build the device and how to introduce the parameters. So again, as Federico did, I will select a molecule to put as a contact from the database. So this is a water molecule. Okay. You can also import a geometry file in different formats or build a molecule by yourself. Okay, and now we need to create an electrode. So in order to create an electrode, I go to create a surface tool. And here we choose a bulk structure, so material from which we want to build an electrode. And here I want to do the calculation for copper. There were some studies of reactions in water when current is applied through copper electrodes. So I selected copper, and here I see the latest constant for it from the database, which is 3.61. You can change it here if you know the optimized constant, or you can first create a project for bulk material to optimize the latest constant. But here I will just use this value from the database. Okay. Now we need to create the surface, so we can select Miller indices for the surface. The number of layers, here the structure is FCC, so I will put 3 layers for periodicity. And the number when you, repetition number in plane. But here for transport calculation, I recommend to use the smallest cross-section for unit electrode set. So to use the smallest cross-section as possible for this moment. And then so if we create a surface, we create structure which is not periodic in Z direction, as it's shown here. But for transport calculation, we need the structure to be periodic in transport direction. Therefore, I tick here that the structure should be periodic along the Z-axis. And then it's also possible to create one-dimensional or two-dimensional structures if you remove periodicity in cross-section direction. For example, if I do like this or like this, so this will be like a wire. Okay, but here I want to perform calculation for bulk material, so I create the unit cells that is periodic in all dimensions. Okay, with that we have our electrode created. Now we can already proceed to build the device. Okay, we select projects that correspond to the electrode structure and water molecule. And using the mouse, I find the tool for merge for transport for calculations. Okay. So the first thing that we see here is that as electrode, copper structure is selected. So as electrode, you can select any structure that is periodic at least in one direction. You can select several projects, and then you will be able to choose the electrode structure among all the periodic structures selected. But here there was only one project with periodic structure, so this is copper. And for contact, I will select water molecule. Okay, and the second electrode is also copper. The second electrode can be selected different from the first one. But in this first demo, it will be the same. Okay, now we can also change the orientation of the electrode unit cells to choose a different transport direction for the structure selected. So, for example, I can change to y-axis. Automatically, the second electrode is also oriented along y-axis. I will go back to that axis. Okay, we can do the same with the water molecule. And we change the orientation, and we can also flip it. Okay, we can move it to use the same position as it was in the previous project. No, but I want here to center it in the middle of the cell. Okay. So now you can see here, this is the structure, and this is left electrode bulk unit cell. This is right electrode bulk unit cell, and this is scattering region, which includes some electrode layers. And there is also buffer layers. So these buffer layers I added in order to deal with charge convergence. So sometimes in transistor calculations, there is a problem to convert charge. So if you have buffer, you can put extra charge on the buffer, and this helps to converge to the right state. And here, so now in the buffer, we have one unit cell. So it corresponds to one unit cell of the electrode, but it can be much smaller, so it doesn't need to be large. I'll put 0.4 for the left electrode and 0.4 for the right electrode. Okay, now we'll update the structure. Okay, now I also see that water molecule is, so the structure is periodic in the cross section. So the periodic images of water molecule are too close to each other. So I need to increase the cross section. I will do it here. So I'll put twice bigger units, size of the unit cell in the cross section, and here as well. Date structure. Okay, so now it looks better. So in principle, we can just adjust the gap a little bit and run the calculation. Okay. So the first thing when you run the calculation, what transport project does is it performs the check whether the length of the unit cells of the electrode and the length of the scattering region are long enough so that the calculation makes physical sense. So in the formalism, in this non-equilibrium green function formalism, we assume that electrode is a sequence of unit cells. And these unit cells can only interact with adjacent unit cells. There is no interaction of atoms outside of one unit cell. And here is the problem that orbitals of atoms outside the unit cell overlap. In order to avoid it, the size of the unit cell of the electrode should be twice longer than orbital extension. And the same also is valid for scattering region, should be larger than twice the orbital size. So what we need to do here is to increase the size of the unit cell of electrodes. So here I opened the settings widget of already created transport project. And now what we will do is to rebuild the structure from scratch. So the same parameters are saved, but now I will say that the length of the unit cell should be twice larger for both of the electrode. And update atomic structure. So now this length of the unit cell will be enough. Also, what I didn't mention is that it's important to include some electrode layers at the contact in the scattering region, because electrons, so unit cell, bulk unit cell of the electrons should really behave as bulk. The Hamiltonian for this part should be bulk Hamiltonian. Otherwise, so if we, and this, some surface layers are needed to describe transition from surface to bulk. If we don't do this, there can be convergence problems. So if you have some convergence problem, try increasing to add some more layers at the scattering region. Okay, so now we adjusted the structure. And what we can also do is to change it manually. So I clicked on that on the image of atomic structure, and I can see it like this in this editor of structure editor. And what can be done is to, for example, to create tips, to select some atoms and remove them. Now we have a tip here, and also here we can do the same. And we can move the water molecule. We can change the position or rotate it. Okay. And now we save the changes. And now if we look in the parameters of the transport project, we will see that we have these tips, and for this structure we'll perform the calculation. We can adjust again the gaps, so the distance between the last surface atom and the molecule, and the same on the other side. But we should not rebuild from scratch, which will remove these tips. Okay, something like this. And in order to run now the transport calculation, we need also to set the voltages for which we want to perform the calculation. So here, for example, from -1 to 1. And 0 voltage is always included. So this is the first calculation that is performed. And then in parameters and calculated parameters, we see the same parameters that need to be set for siesta, exchange correlation potential, real space mesh cutoff, K-point sampling. Basis set, here can be basis different for 2 electrodes. It's important that there are different mixing parameters for electrodes and the device. So electrodes are small, so for them we can use a normal mixing parameter, but for the whole device, it's better to use a smaller mixing coefficient, which is by default is 0.05 here, but in some system it's needed to decrease further in order to get convergence. There are also some parameters that are only needed for transistor. So here in device section, that is, for example, whether we want to update the whole density matrix or only cross terms between scattering region and electrodes or nothing. And charge correction, as I said, it's needed to help convergence. So here we set buffer, so we put extra charge on buffer for 0 voltage calculation. If you're advanced user, you can also adjust integration contours for green function, the number of points, minimal energy, etc. And you can also use the customized FDF, for example, option. So you can see here the input FDF file for transistor, which is quite big. You need to include a lot of blocks about chemical potentials, contours, etc. For example, if I want here for one contour to use a different number of points than for the other, I can just edit it here. Interpret. Okay, so you can see that FDF file for transistor is quite complicated, and the sub really helps to prepare it with no deep preparation. Okay. Okay. Now we go to the run widget. Okay, again we can preview what is in the input file if we want, and we can run the calculation either on the local machine or on remote cluster. Okay, I have this project already ready. This project completed. And in the run widget, what you see when the calculation is running, that you can see the task output, which shows that which steps of the calculation are performed. So the first thing to perform is this length check. That here it passes because we have long enough unit cells for the electrodes. Then the calculation for each of the electrodes, and then calculation for different voltages starting from zeros. And in the calculator output, you can see the current output file. Here's the last output file when the calculation is finished. Also, you can go to run directory. And in the output, you can find the folder with data for electrodes. So these are density matrix and output, siesta output. Okay. And the same for different voltages. So the folder of voltages. 0 voltage calculation. So here first it gives some parameters of the parameters from the input file, basis set, setting basis set, etc. And then the first thing that is done, it runs the single point calculation for the whole device. So first the normal siesta calculation is done. Here we look at convergence of density matrix and Hamiltonian. Okay, when the convergence is reached, then trans-siesta calculation is started. And here, additionally, you have to look at the excess charge that should also be converged. So at the end of the calculation, we see that density matrix, Hamiltonian, and charge are converged. And this is good. Otherwise, the calculation will fail, and you will see that the status of your project is failed. So you can access here also the output files for other voltages. Okay, and now I press the Analyze button, and here what we will see is just the list of files corresponding to density matrix and Hamiltonian that will be used in TB-trans calculation. So what I need to do is to create transport post-processing project. Okay, and here it is created, new transport post-processing project. In the parameters, we can edit the voltages that for which we want to run the TB-trans calculation. We can add more values because Hamiltonian and from trans-siesta calculation can be interpolated. So we can set here, for example, 0.05. Okay. Or we can remove some values if we don't need them. Okay. And then we can also select the properties that we want to compute. Here we can select those for electrodes from spectral function, those from the green function, projected density of states, K-point resolved transmission, and the number of transmission eigenvalues that contribute to transmission. So at this moment, we don't have visualization of eigenchannels, but we can only check how many eigenvalues contribute to the plot of transmission. Okay. And in TB-trans calculator widget, you need to check the K-point grid. Normally, it's better to use a denser grid than for transport calculation. Okay, it's needed to check that the results are converged with respect to the K-point grid. Then to select the energy grid for which to compute transmission, and green function imaginary part, which will determine smearing of your curve. Okay, with that, we can run the calculation. Okay, again, I have the results here. So this is output of TB trans calculation. Okay, so now we see the analysis widgets of final results. This is current voltage curve. So this is non-spin polarized calculation, but if we had spin polarization, we would be able to see spin polarized currents. So there would be macro curves. And transmission, we can compare transmission at different voltages, for example, at minus 0.5 and at minus 0.1, how the transmission evolved. We can also, so this is the plot, and here down you have the information about the lines. So you can edit the color of the lines, for example. So I'll put here it. Okay. Now we can also compare how transmission of the device compares with transmission of bulk of pure electrodes. So we click show bulk. So this is transmission of electrode 1 and electrode 2. The axis is on the right, so it's much higher than of the device. Normally, you need to check that there is no transmission of the device in the region where there is no transmission of the bulk electrode. Okay. And we can also plot. So what is the contribution of first eigenvalue? Okay, and of the second one is 0. So here only one eigenchannel contributes to transmission. And then we can also check K-point resolved transmission. So for a given voltage, which is here 0.5, minus 0.4, we select an energy for which we want to plot, for example, this peak. Okay, so we can see how different K-points contribute to transmission. So this is the axis for this reciprocal space. And there is also information on density of states for different voltages. So here we have plotted density of states for electrodes and for the device at voltage minus 0.1 volt. From comparison of density of states computed from spectral function and from green function, we can also find density of states corresponding to bound states, and this kind of information that is available from TB trans. And we can also perform analysis of projected density of states. So you can choose some atom indices, species. For example, here I will select just, for example, hydrogen and copper on the right electrode, and some orbitals like S and D orbitals at the curve. So this is a contribution of these orbitals from these atoms. You can also select atom indexes if you want. So as you see, that ASAP really helps to perform these complex transport calculations using TransIesta, and to control the calculation and to visualize the results. And we are constantly working on including new features. So what we showed is what is available now, but there are more features that can be, there are more properties that can be available using TB trans, and we are working on this now.